Good afternoon, everyone. Thank you for taking the time to join. We have 2 after now, so I will begin by welcoming you all to this, the 24th webinar in the NRAP Webinar series. It's been a little while since we've held a webinar. We did, however, have a workshop not too terribly long ago, virtual workshop that is, but definitely want to welcome you and introduce our speaker today, Dr. Quanlin Zhou from Lawrence Berkeley National Lab, works in the Geosciences Division, where he's a staff scientist. He has well over 20 years working with experience and expertise in subsurface hydrogeology. He's been working about 50 years on a wide range of topics related to geologic carbon sequestration. Today, he will give us a presentation on a body of work that he's been developing over the past few years on the topic of thermal fracturing induced by CO2 injection into the subsurface. And with no further ado, I will pass it off to Quanlin. Thank you very much.
Okay, thank you, Bob. So today I talk about the thermal fracturing induced by CO2 injection, field evidence and analogs, theoretical solutions, and the potential risks. So I have focused on thermal fracturing at CO2 storage sites for 10 years by learning a lot from analogs in non-CCS fields, and by collecting monitoring data from several CO2 storage sites and trying to understand the behavior of injection pressure. 2 years ago, Bin Chen joined me with support from NRAP. We started to focus on fundamental understanding of thermal fracturing in a systematic way. He has done all the modeling work presented today. So I will first show field analogs of thermal fracturing in geothermal, EGS, like enhanced geothermal system, water flooding, and unconventional oil and gas fields, and field evidence from 3 CO2 storage sites. Then show fracture patterns from laboratory experiments, and then on systematic theoretical studies for 3 scenarios, including half-plane thermal fractures from a hydronic fracture, radial thermal fractures around a horizontal well, and then longitudinal thermal fractures along a vertical wells, all with heat conduction only. So finally, I will point out the potential risks of thermal fracturing. And so our solutions are good for permitting and fast prediction because we only consider thermal conduction without heat convection. So for a site-specific application, numerical modeling of coupled thermal hydromechanic fracturing processes can be used to match field observations. This is the last but more complicated scenario. So from this, these field analogs help us to develop 3 scenarios for our study. Like thermal fracturing for the first 3 applications can be tracked back to 1970s and 1980s, but has been overlooked by CCS community. So the first generation EGS proposed in the early 1970s by Los Alamos pioneers includes the large diameter penny-shaped hydronic fractures for water circulation, and also parallel secondary transverse thermal fractures for enhancing fracture matrix heat exchange. So that's the thermal fractures. That's the hydronic fractures. So this is our first scenario of half-plane thermal fractures. So thermal stimulation by cold water injection into hot geothermal reservoirs has been used since 1980 to enhance wellbore injectivity and productivity in several countries. So the figure shows such enhancement by cold water circulation that can be attributed to creation of new thermal fractures and the opening of closed natural fractures. Thermal stimulation can often take a few hours to several months. So these are field analogs from water flooding fields. So the first ones I pay attention to. There are a lot of data on fracture gradient changes with the seawater or produced water injection, vertical or horizontal wells, and different stress orientation. So the figure shows a higher injectivity for colder seawater injection than produced water injection. So these are the only seismic images I know to show the combined effect of hydronic and thermal fracturing in horizontal injection wells over 10 years. So the top figure shows data with the alternating horizontal, like this is the production well and the injection well, production and the injection wells. So, but the bottom figure shows this the amplitude modeled with the calibrated rock properties. So their model was based on randomly distributed hydronic, like this is hydronic and the thermal fractures. Otherwise, the match was not good. So they point out, they compare different models, and they point out that this model is the best for the history match. So the left figure shows cyclic cooling of cased hillside section of a horizontal well during 14-stage hydronic stimulation in the high temperature Eagle Fault. The cooling is up to 120 degrees C, and I believe thermal fracturing occurred. But the oil industry has not paid attention to thermal fracturing during hydronic stimulation of unconventional fields. This case helps us develop the second scenario of radial transverse thermal fractures. Now switch to CCS. So most recently, field evidence of thermal fracturing from CO2 storage sites has been reported. At Aquistore, CO2 injectivity increases with cooling, as shown in the top figure. So our calculated dimensionless effective confining stress T under injection condition is 0.66, less than 1, indicating that thermal fracturing occurred. So their numeric modeling with the local mesh refinement around the injection well also show the thermal fracturing. So at Erdos, the top right figure shows injectivity enhancement with time because of the cooling induced by liquid CO2 injection. After the first year, more than 80% of injected CO2 was through the fractured 10-meter thin layer at the top, bypassing the majority of the planned 800 meters storage formations used to enhance injectivity, because at this site injectivity is very low. So for cornfield, we can see injected CO2 flows through the channel S11 is shown by the flow meter log during CO2 injection, and by temperature log before CO2 injection. So injection pressure, that's the injection pressure, pressure increase, delta P, changes from like 60 bars to 90 bars, when injection rate changes from 3 to 8 kg per sec. So no good pressure match was achieved without considering the THM fracturing effect with a cooling of 60 degrees C. So now let's move on to the laboratory experiment. That's one example by Yu Wu. So you can see here is a wearable, and that is like a radial transverse thermal fracture induced by liquid nitrogen injection. Here are fracture patterns from laboratory experiments under no confining stress. So we learned a lot from their studies. For example, one thing is we can know the fracture pattern with the propagating fractures and the arrested fractures. And the other one is stability analysis for fracture arrest. So we use this the same stability analysis in our theoretical studies. Now let's move on to the more technical part of our modeling. So that is theoretical modeling and the solutions of thermal fracturings for these three scenarios. Again, like half-plane thermal fracturing fractures from a hydronic fracture, radial thermal fractures around a horizontal weir, and then longitudinal thermal fractures along a vertical weir. So so you see this 3D images of these scenarios. Finally, we compare the solutions for these three scenarios. So maybe here I slow down a little bit because here is more difficult to understand, because for the first scenario, we have this like horizontal like hydronic fractures with an elevated pressure PF and the surface cooling delta TS, and we also have this like a semi-infinity half space for the rock mass. So that means the domain, the system, we have a confining in situ confining stress sigma 0, and we also have like a far field effective confining stress sigma E. So reservoir cooling by heat conduction in this direction induced thermal stress in the Y direction that initiates and propagating thermal fracture in the X directions. So some fractures are arrested at a different time and a different distance due to interfracture stress interaction, leading to a hierarchic pattern of propagating and arrested fractures with dynamic spacing, like that's spacing D, and the length, and then this is aperture fracture aperture profile. So the key question is how to efficiently simulate fracture propagation and arrest in order to predict the evolution of fracture length, dynamic spacing, aperture profile, and fracture pattern. So here is the governing equations and the solution methodology. Thermal stress is calculated by the analytical solution for the temperature field, and in the elasticity equation, we have the fracture-induced elastic stress. That is the hyposynchronous Green's function, and then we have a let's see. We have a thermal stress, we have a effective confining stress, sigma EC. So of course we have a like fracture propagation criteria, and in addition we have a fracture arrest criteria. So we use a non-dimensionalization to scale the different property like variables. And then now we have a dimensionless fracture length L, fracture spacing D, and then fracture aperture omega. And then we only have one model parameter T. So that is the ratio of the effective confining stress to the thermal stress at the surface, cooling surface, or the hydronic fracture. So this is the dimensional governing equations, and then we use the DDM to describe these equations for all the fractures. You see, for yeah. Now let's say we have the solutions for single fractures, constant space in the fractures, and the dynamic space fractures. So for single fractures, so the solutions are all these profiles or type curves, yeah, with the time. That's the time. And then late time, the profiles are indeed like a straight line. So that means well, at late time, we can use the scaling law to do the modeling and the fast predictions. So this scaling law was derived for some special case, like a t equals 0 or t equals close to 1. And then we have this formula. So that means the fracture length is based on the square root of t. So that means so that is the k. And then we have a scaling coefficient that based on these two stream cases, we have an analytical expression. So that solution is like this for solve the single equations, and then pretty much these two can be used to cover the whole the range of t from 0 to 1. So for constant space fractures, we can see you see the propagation follows the single fractures and they deviate from the single fracture solutions with slower propagation speed. So that you see that is the effect of D. This is spacing. You can see you have a smaller spacing, and then this stress interaction is stronger, and then you have a smaller fracture length. So that, but for all this, we also have this scaling law for late time propagations, again with the square root of t. But the scaling coefficient depends on d also. So, but here is very hard to understand even during the review of our papers. Now, for example, initially we have like a 64 fractures initiated at the cooling surface, but at some time, and then that is the critical condition. So half of them are arrested, but the fracture spacing doubled. And again, propagate is a stable propagation, and then arrest again and again. So after 4 steps or arrests, we only have 4 propagating fractures all other factors are arrested at a different time. So in this figure, so that is the boundary, like we call the arrest line between unstable and the stable region. And then this center line here is also a approximation solutions. But on the right side, you can see the pink are the solutions for dynamic spacing. So we can see from here, we compare all these three solutions. And then we can say interfactor stress interaction, slow down fracture propagation by comparing single fracture and constant space fracture solutions. Fracture arrest with fracture spacing double leads to weak stress interaction and increase the fracture length by compare constant space and the dynamic space fracture solutions. So now move on to the type curves. So that are solutions for dynamic space fractures. That is fracture spacing as a function of distance x and time, and the fracture length and the surface aperture at the hadronic fractures. So you can see all these like type curves. So that's the solutions because we only have one model parameter. And then, so we also get the scaling law again as a square root t time, but the scaling coefficient is different. Now for the application, we can see we use the Utah Forge data for our application and the validation. So the rock properties and the boundary conditions in the red boxes are converted to the only parameter t. So we know that is 0.11. So that means we can use this parameter to get our like theoretical solutions, like dimensionless, and then we convert it to dimensional solutions. So that is they show that is the pattern. So from here we can see for the validation that is all model 1 fractures. The pattern are very close to each other, but here we have a sharp change, but here is more smooth change. So here are for the fracture spacing, we have 3 solutions. The stepwise fracture spacing, like in the fracture pattern, and also continuous change fracture spacing change. So that is a rest line, and this is central line. So the central line is very close to the numeric solutions, the indot. For fracture length and also surface apertures, we can see the arrest line solution. So the solid red are very close to the FEM solutions during the CO2 during the fracture propagation. You see, for propagation and arrest, propagation and arrest. But this one they continue to propagate. But this is the aperture simulated by numerical modeling. So here, like for this short-term fracture propagation, we can use our computer code to do simulations. But for long-term propagations, we can use very simple scaling laws to do the propagation, to do the prediction. But here, sometimes, so when you have the water circulation, the pressure is increased in the hadronic fractures. So so that means increased from that is the in situ pressure and the increased pressure, and then we also calculate the T. So that means we again to do the theoretical modeling with this value, and then you can see the prediction the different profiles. So the here is like that thermal stress is the driving force again for thermal fracture propagation. So not the enhanced or elevated pressure. So of course, in our modeling, we assume the fractures are mode 1. So now we did a comparison with the mixed mode FEM modeling, and we can see the match. Yeah, you see, are very close to our mode 1 theoretic solution, and this is the fracture pattern. Even though the pattern with the curvature, but the solution for the like type curves or profiles are very close to each other. And then now let's move on to the radial thermal fractures. I think I need to speed up. Now we have like a horizontal wave here with also with cooling and elevated pressure. And but in this case, we can consider cased web or open or perforated web. So here are the fracture pattern. So I think yeah. Now the difference is here. The temperature field is different because this 1D radial flow some temperature in Laplace domain, and then we have intra fracture elastic stress. That is from the literature. We derived this for multi-fracture interaction. That is canal. And then in this case, we have same thing here and the same thing here. But we have one more parameters. So that means A is a dimensionless web radius. Now for single fractures, you see, these are all profiles here, but the scales are the same. So you can see the same different A, like radius, share the same slope, but the different T, the slope is different. So you can see that here. And then we also have like 4 propagation regimes. You can see here. That is half plane fractures. And then that in the middle, that's unique for radial fracture with a web. And then after this is like pen-shaped fractures. So that is an analytic solution. And after this is scaling law. So I think maybe here one thing is the scaling law. The scaling exponent is 1 minus tau half of this. And then that is the dynamic space fractures. So the top one with different T, but the same A, you can see that is the spacing, fracture length, and the surface aperture. But the bottom is for different A, but the same T. You can see that is a very large like a web or the web like a diameter or radius. So that means our solution can be used for large diameter tunnels. So for application and validation, we also use Utah Forge data. You see that is a fracture pattern with mode 1 and also mixed mode. You can see the curvature is not significant. And then we pick up the fractures. 4 fractures we compare with this. And this is for spacing. This is the average spacing for the FEM solutions. And you can see the central line solution is very close to the FEM solution. And here this like a rest line fracture length solutions, and then a rest line surface aperture solutions are very close to that. And so that means for this type of application, we only need these two parameters, T and A. So for applications with some weighted pressures, we calculate T. So again, we do the simulation and we get curves, type curves or profiles. You see the effect length and effect surface apertures. And then here is very interesting. We use our solutions to do this cyclic cooling. So that is injection and shutting, injection and shutting. That is a kind of hydronic simulation case. And then here we have with some assumptions. This is the weighted pressure and this is in situ pressure. You can see we can do the simulation for that. And then this is like a continuous cooling with a constant delta T. So now I think this is the final scenarios in our case. So that is like a longitudinal thermal fractures. So in this case, it needs to be more complicated because we have we have to consider two stress, like a horizontal stress. That is the maximum horizontal stress and the minimum horizontal stress. But in this case, if the anisotropy is strong, we will have two wind fractures. So that's two wind fractures. But when the anisotropy is weak, so kind of K kappa equals 1. So we will have this dynamic and constant space fractures. So the idea is like that initially you have dense fractures around the wearable wall, and then but some fractures were arrested. But away from the wearable, the distance is bigger, and then finally you have this constant angular spacing. So that means you have a finite number of thermal fractures propagating with time. So like this is for this isotropic stress case. You see this again is something propagate and arrest, propagate and arrest and propagate. But now that is propagate forever. So because there's no change in the angular spacing. So with time. So here another case like for fracture length, you can see the pink solution and then the blue solution. That's a combined solution for the isotropic case. And then, but for any anisotropic case, this solution should be bounded by the two wind solution and this like a combined isotropic solutions. That is the concept for longitudinal thermal fractures along vertical wearables. So now we have two wind solutions, same, but different parameters. You can see here, same solution, and we also have a scaling law, but this time the scaling exponent is different now. And so that is the scaling law. You can see it later. And so, but here you see, we get these solutions and then we fit this data because we know this format. Okay, we fit this data, we get this scaling exponent. But here is for the scaling coefficient. So it's functions of A and T, you see here. So this is a constant and dynamic solutions. This is constant space solutions for different parameters again. So all different type of different type curves. But for dynamic space fractures, you can see after several times the spacing is constant, and then you switch to the constant space solutions, and then that is so this is kind of the special things for longitudinal fractures. So Here you can see this is the fracture pattern. So, and then when this A is very small, you may just have like two propagating fractures at nighttime. But here you have 4, 8, and 32. So that means so this is more or less like a Weber size, okay? This is for Weber size. But this is, you see, 10 times of Weber size, 100 times of Weber size. You can see that. And then for the application, again, we use Utah Forge data with the parameters. But now we assume that is stress isotropy, carbon equals 1. And then we have this like a fracture pattern. And then we have a fracture angular spacing, fracture length, and the fracture surface aperture. You can see that is the transition. And now here you have another transition from like a dynamic to constant space solution. And again, that's pink and to red. That's a transition. So that is the kind of the again this for the application. But we can see when compared with the numeric solutions, we can see the pattern and the spacing length and the aperture, surface aperture, all very close to each other for this. That means all solutions are validated. But now, for the site-specific like stress anisotropy, and then we did the finite element modeling, and then that is you can see the pattern at nighttime, but the early time, so you see you have multiple fractures, thermal fractures. And here we have the two-wing solution and this combined like a multiple fracture solutions, and then the dots are like numeric solutions. You can see the transition, they bounded by these two solutions, and the late time close to the two-wing solutions. And then that is for a surface aperture. So now in this case, we don't have for any parameters. We have to use the two solutions. So that means for strong fracture anisotropy, we can use like a two-wing fracture solutions. For weak stress anisotropy, we can use like the multiple fracture solutions. But for intermediate fracture anisotropy, we can use solutions to bound the actual solution. So that is kind of the concept for the modeling. And so finally, that is the comparison. For that, I think that is the again for the Utah Forge side with the in situ stress and the pressure. We can see this is the half plane solution, and this is radial, and this is the two-wing solutions. So you can see, and then that is the scaling law, and so we say we have F and Q. So that is this form, and then we can see that's the Q equals 1 for half plane, and 1 minus 4 T equals for radial, and 1 minus 2 T for longitudinal solutions. And similarly, the scaling coefficient is more complicated, but still we can get the solution and get the scaling coefficient. Now, that is the last part of this talk. I think I have like 7 minutes. So of course, we know that thermal fracturing, the benefit is enhanced CO2 injectivity. So that from all the different analogs, we know that, yeah. But on the other side, injective CO2 flows through the newly created fractures, bypassing other sandstone layers and formations perforated or otherwise good for storage. It's happened at Erdose because after thermal fracturing, majority of injected CO2 flow this one and all bypass this very thick storage system. And that means we reduce like the storage capacity is reduced because all this bypassed. And but at the same time, for a horizontal weir, maybe you have injected CO2 all through the fractured section of the horizontal weir, bypassing majority of the network for CO2 injection. And then the second risk, type of risk is the CO2 leakage through thermal fractures. So you see that can happen because this is a cased weber in caprock, but you still have thermal exchange and it's like a fracture propagating. So that sometimes is big because the thermal fractures can be tens of meters and long in length with the aperture of 1 centimeter over 50 years of CO2 injection. So of course, the fracture length and the aperture depends on site-specific conditions. But now here is the final map. I think maybe Solomon presented this the location of 5 carbon-safe phase 3 project site. When I put on this map at depth, like a temperature at depth, and then we can see the red that so this Sandra and the dry fork and the San Juan Queen Basin, and also this Timber. They're all located in high temperature at depth. So that means maybe thermal fracturing is possible, especially during the high injection rate for the future CO2 injection. But you know that the cornfield, we already have the thermal fracturing observed. And then here, that is the Aquistore, very similar, like a temperature, more than 100 degrees Celsius. So that's kind of, when we put all this together, we know, okay, thermal fracturing should be an issue for CO2 injection in many areas with high temperature depths. I think maybe I spend 1 minute here. So of course we know the thermal fracturing is not new, especially for other fields like water flooding, hydrothermal field. Sometimes they use thermal fracturing to get benefit, like enhance productivity. So, but of course, recently we have a thermal fracturing from induced by CO2 injection reported at different sites. Yeah, but overall, so the thermal fracturing and the potential risks are still overlooked by CCS community. And so, okay, that is the more technical part. I say, finally we develop different solutions for different scenarios. We can use that solutions and the scaling law for fast predictions. But so here you see the potential risks for CO2 leakage. So vertical thermal fractures in high temperature caprock. That is one potential, and the other potential risk is like reduced storage capacity and efficiency. That is another one for that. Yeah, I think that is all. That is I think we published one paper, and this is I think very close to the end, and we have 2 papers under review. So that is the and from that I think now it's time to take questions.
Yes, we'll open it up now to questions and Q&A. And we've seen a couple of comments come through already in the chat. Participants, please feel free to unmute yourselves to also use the raise hand function and use the chat. We had a question come through offline from Talib Fayed. Are there horizontal wells active in Ordos, Cranfield, and Aquistore Decatur? If most CO2 storage wells are vertical, then radial thermal fractures around horizontal wells may not be a concern, and only longitudinal fractures have to be looked at. That's my pronunciation.
No, wait. I missed the question. Could you ask again?
Certainly. It starts off, are there horizontal wells active in Ordos, Cranfield, and Aquistore Decatur?
So, no, that's vertical wells. So for CCS, I think the like 3 horizontal wells are in Sana, Algeria. That's the only 3 horizontal injection wells.
All right. A question has come through from Preston Jordan. What is termed a gas chimney through intra-information shale baffles developed at Leitner? Could this actually be due to thermal fracturing? And Preston, feel free to
this is a shale baffle development. Okay. Sniper, we know the temperature is very low, so that's not the case. We know the temperature is about 30-something degrees C. There's no much, but the chimney is far away from the injection well. You know that for the fracture length, so that's not the case. But so again, the thermal fracturing around the wellbores, very near the wellbore. So I know in North Sea, the first horizontal wells, that is for like EOR. So the horizontal well was fractured, sometimes with very high injection pressure, and with some kind of thermal effect over there. So that is one case, but not for Slapler. So the last one is how is thermal fracturing detected during field injection. So okay, so like from the map, like a temperature at the depth map, you can see somewhere the reservoir temperature is very high. So that means we should be very careful for CO2 injection. If we have this bottom hole pressure temperature gauges, and then we can see if it's possible to get fracturing, because now the parameter T is the key. That is the ratio between the effective confining stress to surface thermal stress. So I think for permitting, that is what we can do. But of course, because okay, I think I should mention this again. The number 4 scenario is more complicated. So that means in the reservoir with higher permeability, you have a heat convection, and like the heat transport with the flowing fluid. And in that case, the fracture should be longer. That is we didn't consider a heat convection for that case. So in that case, maybe pneumatic simulation is the only way we can do modeling.
We have another question coming from Talib. Is fracture arrest good or bad for storage capacity and storage efficiency? In horizontal shale wells, hydraulically fracture-driven interactions in offset wells may actually increase performance and EUR in offset wells in some instances.
Yes, for that for that seismic images, so they do for okay, wait, let's put it that way. For water flooding, for EOR, so the thermal factoring is good for some aspects. And then I know the one case, thermal factoring occurred in the sealing units. So that is one case I know, and then that is bad, okay? But in the reservoir, if you have a thermal factoring, you are okay. But if the thermal factoring occurs in caprock or sealing units, you will have a problem. So that, of course, for injectivity, yes, we have a benefit. But on the other side, for leakage risk, we may have a negative impact from thermal factoring.
All right. Question from Gavin Liu in the chat. He's not sure if he missed you talking about it, but compared to horizontal wells you mentioned from unconventional geothermal, how much overall impact of thermal impact on usually CO2 wells regarding the storage versus leakage?
So I think that is of course for EGS, for geothermal, so you know that from the analogs we know they get benefit from that, yeah. But for CO2 is different, and then for geothermal, even for EGS, maybe right now they didn't pay attention on the caprock issues. But if the caprock is high temperature, we may have a problem for that. But right now, it seems there's no reported analogs for that part. But we see from the processes, if the caprock temperature is very high, we may have trouble for that. But from the field, of course, that's case by case, yeah, site by site. So that's yeah.
From Faro, another question in the chat. Is there a published report or paper available with these results that can be cited?
Oh, so again, I think our papers will be published one by one, because I think the first paper for the half plan thermal factors, so we submit in December 2020. Still under review, but the last round is 3 minor revisions. I think we submitted, so should be very soon. I think will be published. And the other 2 are still under review. So once they are published, I think I can share with you guys. Yeah.
All right. We have one more question come into the chat. I'm also knowing that we're coming up on the hour. This is from Talib. Again, in Alpine, bottom hole temperature is only 71 Celsius, but the difference between injected temperature and bottom hole temperature is 30 to 40 Celsius. So, if we were able to keep this delta T small, will this be an advantage and minimize risks from thermal stresses and cooling effects?
Yeah, so for Alpine, you see the seismic image. They may not have direct evidence of thermal fracturing, but in Alaska, the temperature, the reservoir temperature is relatively high compared with the injected water temperature. So It seems from their study, like only, their study is kind of, they have to consider thermal fractures, like a combined effect of thermal fractures and hydronic fractures, because in that, sometimes they don't follow like a CO2 injection practice, because for CO2 permitting, so we have to control the injection pressure smaller than fracture pressure, fracturing pressure. But for EOR, like water flooding, sometimes they always keep like injection pressure higher than fracturing pressure. So that is kind of the case for opening. So yeah. So like for those, the temperature is just like 52 degrees C, but they injected liquid CO2 sometimes with minus 15 degrees C. That is like the contrast for the injected CO2 temperature and the reservoir temperature. That is the key.
All right, our final question in the chat, and then we will wrap up. This is from Paul. Given delta T is the main driver for thermal fracture propagation, which starts from the wellbore, is the risk of cold CO2 traveling to the caprock that significant for the delta to be large enough to cause thermal fracturing in the caprock?
So, okay, in INSANA, some groups did modeling and to see if the thermal stress and into the caprock instability. They did some modeling, but of course, they didn't consider thermal fracturing of that. So in water flooding like field, they usually control this kind of fracture propagation in the reservoir because of some maybe stress change between different formations. So yes, you have a possibility for that, but remember, keep in mind, so thermal like a temperature transport is slow or not that fast. So maybe that is kind of the reason why like for INSANA, the Princeton group and the like Spanish group, they did some modeling and then show this like thermal stress induced shearing. They focus on that part, not the tensor fracturing.
All right. Well, that's all the time we have today. Thank you so much, Dr. Zhou, for your presentations, and thank you, participants, for your questions and comments. And have a wonderful day, everybody.
Thank you. Bye-bye.